Welcome to International Advanced Subsidiary Physics Program. I am Sajin from Center for Higher Secondary Education. Unit 2, Waves and Electricity. The total duration for this paper is 1 hour 30 minutes. Total marks 80. Here we can see a QR code. Students, please scan this QR code and mark the attendance. Let's start the lesson. In 1887, Heinrich Rudolf Hertz, one of the famous German scientists, he discovered one phenomenon. He found that some metals are emitting electrons when an electromagnetic radiation of certain frequency is falling on the metal surface. But he couldn't explain that phenomenon. Even many scientists failed to explain. Nobody could give a satisfactory explanation for that phenomenon. It was a headache for the scientist. Later, after many years, one scientist came. He explained this phenomenon. He even got the Nobel Prize. What was that phenomenon? Who was that scientist? That was photoelectric emission. And that scientist was Albert Einstein. And Albert Einstein explained this phenomenon using one mathematician's theory, Max Planck. That was the name of the mathematician. Today in this session, I am planning to discuss photoelectric emission, equations, the photoelectric equation, then some terms associated with photoelectric emission. Let's go through the syllabus specification. Here first we are discussing behavior of light in terms of photons. After that, photoelectric equation, then energy levels, then finally we are discussing stopping potential. So let's start the topic photoelectric emission. So emission of electron from the metal surface, electromagnetic radiation of certain frequency falling on the metal surface. How Einstein explained this photoelectric emission? Einstein said electromagnetic radiation is falling and electrons are emitting. Einstein said this electromagnetic radiation consists of small packets of energy. Each packets are called photons or quanta. That is why this branch is called quantum mechanics. And what is the behavior of this photon? So this is the definition. If they are asking a question, you can give this definition. What are the properties of this photon? What is the speed of this photon? Of course, I said photon electromagnetic radiation consists of photons means the speed of the photon is same as the speed of light. That means speed of electromagnetic radiation. And what is the mass? It has no mass. How about the charge? This photon has no charge. So the conclusion of this photon, the nature of photon is electromagnetic radiation consists of small packets of energy and the speed of the photon is 3 into 10 to the power 8, no mass, no charge. Now we can go to electromagnetic spectrum. This spectrum is very familiar to you. Electromagnetic waves arranged on the basis of wavelength or frequency. Here you can see when you are moving from left to right, wavelength is decreasing or frequency increases. But here there is a question, visible light. You can see the visible light. Visible light, how the visible light is arranged. You all know visible light means VIBGYOR. Violet is there, indigo, all the colors red. Which color is having highest wavelength? Here I can give a tip. Look at that electromagnetic spectrum. And in that spectrum, left side of visible light is infrared and right side of visible light is ultraviolet. So red is coming very close to infrared and violet is coming very close to ultraviolet. So it's very clear, red is left side and right side is violet. So VIBGYOR spectrum also arranged on the basis of decreasing wavelength. Red is having the highest wavelength. Come to the point. Here, just now we studied electromagnetic radiation consists of photon. if you are considering, according to Einstein, if you are considering two waves, infrared and ultraviolet, what's the difference between these two waves? Of course, frequency or wavelength are different, but in terms of photon or in terms of energy of the photon, are they same? No, that was the Einstein's main equation. Einstein said energy of each photon is directly proportional to its frequency. That means if you are comparing infrared or ultraviolet, both consist of photons, but which photon is having highest energy? No doubt ultraviolet, because its frequency is greater. So Einstein made an equation, energy E is directly proportional to frequency. You all know energy is directly proportional to frequency means we need to remove the proportional sign. So here we are using a constant. To remove the proportional sign, we are using a constant. Now the equation is E is equal to h into F. Now you can guess that name. H is Planck's constant. I have mentioned this name before, the mathematician Max Planck. To honor that scientist, still we are using the name Max Planck's constant or Planck's constant. Its value is 6.63 10 to the power minus 34 joule second. We don't have to by heart this figure, it is given in the formula sheet. Now the equation E is equal to hf. How can we replace that frequency? How can we include wavelength? We all know the equation V is equal to F lambda, where lambda is the wavelength. Instead of V, here we can put C, where C is the speed of light. So if you are making F as a subject, so F is equal to C over lambda. So the new equation is E is equal to hc over lambda, right? Now there is a question about photon. One photon is falling and one electron is emitting. If 10 photons falling, 10 electrons are emitting. So the question is, you are given two colors. Two colors means brightness is different. Suppose you are given two red color, but one is bright red, other is dim red. What's the difference between these two colors? Since both colors are same, red means they have same energy. But what is the difference? One is bright and other is dim. So what's the difference? Bright means it consists of more photons compared to dim. So the total energy of bright red is greater than total energy of dim red. Come to this point. One photon can emit one electron. 10 photons can emit 10 electron. So my question is, number of electron emitted is proportional to what? Number of photons falling. That means number of electrons emitted per second is directly proportional to number of photons falling per second. Number of photons falling per second is called intensity. So from this concept you are getting a very important result, that number of electrons emitted from the metal surface per second is directly proportional to intensity of the electromagnetic wave. So this result is very important. Of course, the higher the intensity of beam of light, the more electrons are emitted from the metal surface. Now there is a question, can all the photons emit electron? What do you think? If you are considering a metal surface, do you think that all the metals can emit electron or all the electromagnetic waves can emit electron? Is there any condition? Definitely there is a condition. The incoming photon should have a minimum frequency. That minimum frequency required is called threshold frequency. Similar way, the incoming photon should have a minimum energy. That minimum energy is called work function. Similar way, there is a wavelength required, but I would like to use the word maximum wavelength. Why I used frequency and energy, I used minimum, but why wavelength is maximum? Because frequency and wavelength are opposite, I mean inversely proportional. Then how can we define the term threshold frequency? It is the minimum frequency of electromagnetic radiation required to just release electron from the metal surface. Similar way, how can we define work function? It's a minimum energy required to release an electron from the metal surface. One more thing, if you are considering a metal surface, threshold frequency, work function and threshold wavelength, these three values are constant for that material. If you are taking another material, that material has its own threshold frequency, threshold wavelength and work function. Why it is different? Of course, atomic structure of different materials are different. So, remember these three values are constant for a single material. Then the connected equation. So, work function, how can we connect? Work function is phi is equal to hf0 or is equal to hc over lambda 0. So, this is the equations for work function. Now we discussed some terms associated. Based on these terms, how can we say or what are the conditions for photoelectric emission? Students still have some doubts about photons, metal surface, electrons. So, I can clear. The incoming one is photon. Its energy is capital E. Its frequency is f and its wavelength is lambda. Similar way, if you are considering the metal surface, work function is phi, threshold frequency is f0 or f0, threshold wavelength is lambda 0. Okay. So, what are the conditions for the photoelectric emission? The incoming photon, what should be the energy of the incoming photon? It should be greater than work function. So, the first condition is energy of the incoming photon should be greater than or equal to work function. How about frequency and threshold frequency? No confusion, frequency of the incoming photon should be greater than or equal to threshold frequency. But how about wavelength? Wavelength is less than or equal to. Remember, wavelength and frequency are inverse. That is why it is less than or equal to threshold wavelength. Is the conditions very clear? Now, based on these terms, I mean threshold frequency or wavelength, how can we define photoelectric emission? Can we just say electrons are emitting from the metal surface when an electromagnetic radiation is falling? It not make any sense. In terms of frequency or threshold frequency, how can we define? Emission of electron from the metal surface when an electromagnetic radiation or frequency of electromagnetic radiation is greater than threshold frequency. So, this is the real definition of photoelectric emission. Now, Einstein photoelectric equation. This equation is very important. They asked so many questions based on this equation, but I can introduce this equation based on one simple calculation. Look at this example. Here you can see a metal surface, incoming photon and emitted electrons. Suppose the work function of this metal is 5 joule. The energy of the incoming photon is 7 joule. So, now based on this calculation, you can guess the incoming photon required minimum 5 joule to emit electrons. That means that photon has to spend only 5 joule, but that energy of the incoming photon is 7 joule. Still 2 joule is there. You know, energy should be conserved. So, how the mathematics is working? Energy of the incoming photon has energy is 7 joule and work function is only 5 joule. Still 2 joule is there. Where is that 2 joule is going? That 2 joule is used to provide kinetic energy of the emitted electron. Now, the picture is very clear. The energy of the photon is using for two purposes. One is to overcome the work function. Second one is to provide the kinetic energy. So, the simple max is kinetic energy is 2 joule. So, the simple max is 7 is equal to 5 plus 2. What is 7? 7 means energy of the incoming photon and 5 is the work function. Of course, 2 is what? Kinetic energy of the emitted electron. So, based on simple mathematics, we can make a very important equation. Photon energy is equal to energy needed to free an electron from the metal surface, that is work function, plus kinetic energy of the electron. And of course, we can write in this equation in different format, because energy we have different equations, like energy can be written E is equal to HF, E is equal to HC over lambda. So, one of the format is HF is equal to work function plus kinetic energy. You all know the equation of kinetic energy. If you wish, we can write HF is equal to work function plus half mv square, maximum kinetic energy. But whenever you are doing the question, students are confusing, because when they are doing the question, the energy is there, frequency is there, wavelength is there, work function, threshold frequency. So, it is confusing. I can tell you the tip that whenever you are doing any question related to this equation, please remember, if you are considering the photon, its frequency is f, its wavelength is lambda, and its energy is E. So, the equation connected to energy of the photon is E is equal to HF or E is equal to HC over lambda. Similar way, if you are considering the metal surface, threshold frequency, threshold wavelength and work function. So, the equation connected to work function is HF0 or HC over lambda. And who is the third one? Here already we discussed photon, metal surface, and who is the third one? Emitted electron. Emitted electron, what is the equation? Kinetic energy is equal to half mv square. So, here there is a question. Do we have to by heart all these constant values? What are the values given in the formula sheet? See, Planck's constant, it is given in the formula sheet. H is equal to 6.63 10 to the power minus 34. C, speed of light 3 into 10 to the power 8 meter per second. M, mass of the electron 9.1 into 10 to the power minus 31 kilogram. And what is the last one? 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. What is the unit of that electron volt? Here you can see energy of photon, work function, kinetic energy. Basically these three are energy. Energy, what is the unit of energy? Joules. But there is a special unit, electron volt. Sometimes maybe work function or energy, it will be expressing in electron volt. So, you need to convert electron volt into joule. Sometimes they are asking to express in electron volt. So, that is the special unit of energy. So, you should know this relationship also. It is also given in the formula sheet. So, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Now, one of the most important graph, more than 3 or 4 times already they asked this graph, kinetic energy against frequency. But before just by hearting the shape of the graph, if you are understanding, it is very simple and interesting. Look at this equation. We have already discussed energy is equal to work function plus kinetic energy. Just imagine there is a metal surface, photons are falling and electrons are emitting. You are doing one experiment. So, HF is the energy of the incoming photon, work function phi is the work function of the metal and kinetic energy. I have a question. Suppose you are using ultraviolet. Instead of ultraviolet, you are using X-ray, you are increasing the frequency. Let us discuss first mathematically. According to this equation, if F increases, that means H is constant. So, the left hand side of the equation increasing. Look at the right hand side, work function plus kinetic energy. As you know, work function is constant for the material. So, it never change. Then how about the next possibility? The one and only possibility is kinetic energy will change. Kinetic energy is increasing. Kinetic energy increases means, you know, mass of the electron is constant. So, speed is changing. From this equation, you will be getting an idea that kinetic energy, maximum kinetic energy of the emitted electron or speed of the emitted electron is directly proportional to the frequency of the incoming electromagnetic radiation. Based on this concept, we can plot a graph. The graph is kinetic energy against frequency. Look at the shape of the graph. As you know, normally directly proportional means it's a straight line graph passing through origin. It's a straight line, good. But why this graph is not passing through the origin? Can you guess the reason? This graph is not passing through the origin because there is an x-intercept. That x-intercept is called threshold frequency. We have studied before, below threshold frequency, no photoelectric emission. So, if the graph is passing through the origin means what is the meaning? At any frequency, electrons are emitting. So, it is very clear, below threshold frequency, no emission. That is why this graph is not passing through the origin. Another thing, HF is equal to work function plus kinetic energy. If you are arranging this equation in the form of y is equal to mx plus c, that means you can make kinetic energy as a subject and equating with y is equal to mx plus c, you can see that gradient of the graph gives Planck's constant. And if you are extrapolating the graph, there is a y-intercept. Y-intercept gives minus work function. Also, x-intercept is threshold frequency. So, here the sharp line is showing the graph of one particular metal. Can I draw another metal values, other values on the same graph? Yes, of course. Here dotted lines are showing that is the second metal. So, these values are for the second metal. Second metal also we can draw on the same graph. But remember, all these lines are parallel to each other. Can you guess why all these lines are parallel to each other? Even you can draw many graphs, but all the lines should be or must be parallel to each other, because gradient of the graph is always constant, Planck's constant, that is the universal constant. But I have a question, how about the y-intercept? Will it be same? You can see on this graph, y-intercept is different. What is the reason? Of course, different metal has its own work function. Why different work function? Because work function depends on the atomic structure. Atomic structure is different. Some electrons are loosely packed, some electrons are very tightly packed. So, its work function is different. So, remember, whenever you are plotting more than one graph, the line should be parallel to each other, but they have different y-intercept. So, all graphs are parallel to each other since gradient is Planck's constant, which is universal constant. The y-intercept depend on the work function of the metal used. So, conclusion is different metals will have different y-intercept, but always same gradient. So, based on these things, how can we make the two results? In photoelectric emission topic, there are two results. The first result already we discussed. Do you remember? One photon can emit one electron. Based on that concept, we made a result that number of electrons emitted per second is directly proportional to intensity of the electromagnetic wave. That is the first result. Second result, just now I explained, kinetic energy, maximum kinetic energy of the emitted electron is proportional to frequency of the incoming electromagnetic wave. So, these two theories are these two results are very important. But if you are checking the past paper, you can see they are asking some questions. For example, if the intensity changes, how it is affecting the kinetic energy of the emitted electron? Don't think that always they are asking intensity changes. One paper they asked, here there is a metal surface and there is an electromagnetic source. The distance of the source is increasing. If the distance increases means, of course, intensity varies. So, the question is, if the intensity changes, how it is affecting the kinetic energy? No doubt, no change, because intensity changes, it is affecting only the number of electrons. Similar way, they asked several times, if frequency changes, how it is affecting the number of electron emitted per second? No doubt, no change. So, the conclusion is intensity depends only on the, or number of electron emitted per second depends only on the intensity. Similar way, kinetic energy of the emitted electron is depends only on the frequency of the electromagnetic wave. So, if they are asking any questions, you can say no effect. Let us wind up the class. I think you understood something. So, good luck for the exams.